This is Software Engineering Radio, the podcast for professional developers, on the web at SE-Radio.net. SE Radio brings you relevant and detailed discussions of software engineering topics at least once a month. SE Radio is brought to you by IEEE Software Magazine, online at computer.org/software.
For Software Engineering Radio, this is Stefan Tilkoff. Today I'm joined by Mark Nottingham. Mark is a very well-known figure in Internet standardization. He has been an editor and co-author for numerous standards, such as WS addressing, the Atom syndication format, web linking, and many more. Most recently, he has been chairing the IETF's working group on the web's core protocol, HTTP, leading both a revision of the HTTP 1.1 specification, as well as the introduction of the first new major version in years, HTTP 2, which is going to be today's main topic. He has also recently been elected a member of the W3C's Technical Architecture Group, which gives architectural guidance to all the various working groups creating specifications at the web standardization body. So, welcome, Mark, to this new episode of SE Radio. And as usual, I'd like to start by asking you to introduce yourself.
Okay, my name is Mark Nottingham, and I chair the HTTP working group in the IETF, and I'm also a member of the W3C Technical Architecture Group.
So can you tell us a little bit about what the IETF and the W3C actually do?
So they're both technical standards bodies. So the IETF has been around for a long time, and they were the body that originally took charge of forming and standardizing the Internet. A lot of the Internet pioneers helped put the IETF together. And from my standpoint, it's the body that owns the protocol HTTP. The W3C is the body that owns, it's an industry consortium, which is a little bit different, but much the same, that effectively owns the web itself. And so that was put together by Tim Berners-Lee a few years after after the web really took off.
Okay. So, the topic we're going to talk about is HTTP, more specifically HTTP 2. So before we go into the details of this new version, maybe you can give our listeners a brief introduction to HTTP, which seems like something everybody should know, but maybe nobody really, or some people at least, do not really know from a more standards point of view.
Yeah, everyone uses it, I think, or almost everyone, but the deeper you go, the more you find, I suppose. I still find things that are new to me about it all the time. So it's the core protocol of the web. We say the web is built on three different things, on identifiers, so URLs, URIs, and formats like HTML, and then protocols. And HTTP is the predominant protocol for the web. And it stands for Hypertext Transfer Protocol, so HTTP. And many people confuse that with transport. Transfer means you're transferring what we used to call entities, or you're transferring payloads around back and forth between the client and server. Whereas a transport protocol is a much lower layer thing. It's like TCP or UDP. And so that's it. It's one of the legs that the web stands on. It's been around since Tim came up with it in the early 90s. And it's been through a number of revisions since then. The most recent is what you wanted to talk about, HTTP 2.
I'd like to talk about some of those things that seem entirely obvious but maybe aren't. So maybe it should be obvious what a protocol is, but maybe it's not. What does the term protocol actually mean?
So there's a lot of history behind that in terms of diplomacy and so forth. But in computer protocols, it's how do two machines or two entities talk, in this case over a network usually. HTTP was designed mostly to be a network protocol, but Roy Fielding, one of the primary authors of HTTP 1.1, will go out of his way to point out it's not just for networking, it's also for things like running off of a CD-ROM drive or in other contexts. You can, think of the model of HTTP as there's a client and a server. How do you fetch things off of the server to get them to your web browser in the common case? HTTP is used for lots of other things, but really web browsers is the primary use case. So in terms of, what is the HTTP protocol, it's the way that your web browser asks a web server for what it needs to show you a web page.
Mm-hmm. So maybe let's get more into this transfer and transport distinction. So what actually is it that a transfer protocol adds to a transport protocol?
So it's interesting. A transport protocol is a fairly low layer thing. I won't call it dumb, but from an application standpoint, it doesn't give you a lot. And that's not to denigrate what, for example, TCP does. There's a tremendous amount of value and complexity in what TCP does in terms of giving you this ordered, reliable stream of information. But it doesn't give you a lot to hang on to as an application. You need to build things on top of that. So HTTP gives you a way to think about how, for example, one message is delimited from another message, so you can tell the difference between one request and the next request on a connection. It gives you things like caching and a common vocabulary to talk about what you want to do. And really that's what protocol is it's a shared vocabulary, a shared way of communicating. And the abstraction in HTTP is fairly high level. You have a common set of methods, get, post, put, delete, and a bunch more. You have these message bodies that you can sling around and have metadata to talk about those message bodies and the HTTP headers, things like content type and, lots of other things that we've added to it over the years. And then you have the responses and the status code that tell you, what the high level semantics, the meaning of that response is. So there's 200 okay to mean that it's okay and that this is what you asked for, and 500 means that the server had a problem and it can't give you what you asked for. All those different things that HTTP gives you in terms of methods and headers and status codes and formality around the bodies gives you the ability to build applications more easily. If you had to create all of that from scratch as a developer, then you'd spend a lot of time getting it right. HTTP is something you can just grab off of the shelf and reuse in your application, and it usually works pretty well. I guess, for folks who are familiar with it, the interesting contrast is with something called WebSockets. WebSockets came around a few years ago, and it is a much lower, it's still an application protocol like HTTP is, but it's a much lower level of abstraction. It's much lower value in that sense. It's basically TCP strapped onto the web, so you just get a bidirectional ordered stream, reliable stream, and between the client and the server. And WebSockets, when I talk to people about it, there are a couple of really interesting applications for it. But once you get past those, it's not really taking off because it doesn't give you a lot to hang on to. You have to build whatever you want to build on top of it. Most developers don't have the time or the expertise to do that. And also you want to be able to leverage other software that has the same idea of what you're communicating about. So, with HTTP, I can go off and take web servers off the shelf, or I can use curl on the client side, or a web proxy or a web cache if I want to scale it out, or I can use different services online, and they all talk HTTP. But with WebSockets, you don't have nearly as much to hold on to, as it were. And so it's a lot harder to build that value.
I always like to point out that I actually consider going from HTTP to WebSockets a downgrade, not an upgrade, even though it's an upgrade on that protocol negotiation kind of thing. So
right, and strictly speaking, WebSockets is more capable. You can build more. There's some things you can build on top of WebSockets that you can't build on top of HTTP, and that's because HTTP imposes constraints. And that's really one of the most interesting things is those constraints, the strictures that they put on you and how you behave when you're talking to someone else do provide a lot of value, that the message is going to look like this and that get means get and post means post and so forth and so on. If you don't have those constraints, it's a wide open field, but you have to build it all yourself.
Mm-hmm. So the constraints simultaneously, constrain you, but they also provide value because they, have decisions. Decisions have already been made for you. Is that a fair description?
Decisions have been made for you, and you're building upon those. You're standing on the shoulders of giants, as it were.
Okay. So, can you give us a brief history of HTTP, of the different versions that were deployed in the wild?
Sure. So HTTP 0.9, which was kind of retroactively named, was the first version that came out of CERN, and that was literally just a request, get this thing, and then you got the response. There were no headers, there was no nothing. Close the connection, start over, and do it again. And so there wasn't really any metadata, there wasn't a status code. It was very primitive. And very soon afterwards, they decided that it was necessary to have more structure around that to add some of that value. And so HTTP 1.0 was kind of developed in the wild and then documented in an informational RFC 1945. And it added headers and it added status codes. And it was very, very much influenced by the design of something called MIME, which is the protocol for mail, for SMTP, for getting email around. But the way that the web uses headers and it uses all these different things is a little bit different from MIME. Different enough where you can't just take a MIME library and repurpose it for the web. So we call HTTP a MIME-like protocol. And that was the design of HTTP 1. HTTP 1 still had a lot of issues, especially around how it used the connections underneath, the TCP connections, the underlying network connections. And it was still every time you wanted to request something, whether it's some HTML or an image or what have you, you had to open a new connection, wait for that to do its handshake, make your request, and then close the connection again after you got the response. And that's horribly inefficient, both on the server side in terms of how it manages its resources as well as on the network and how the network is utilized. And so they built an extension once the web started to take off, once it got really popular, and we're talking 1994-ish, called Keep Alive, where you could reuse the connection, and then make more than one request on a connection. And that was pretty much a hack, but it worked. It had a lot of corner cases and problems with it. And so, when HTTP really started to take off, they decided to, make it more formalized and start work on HTTP 1.1. And that was done in the IETF in a working group, the HTTP working group. And that spent a couple of years, working under a tremendous amount of pressure to try and document a better version of this protocol that was taking the world by storm. And so HTTP 1.1 it formalized this mechanism of Keep Alive. It allowed you to reuse a connection. It made some other changes as well. It had a more formal caching model. It had a few other interesting things like HTTP pipelining, which unfortunately never really took off. And then it, went to market. It was written down really in a rush, because there was such pressure to get it done. And it was written down by a committee. I had a lot of different people contributing. So HTTP 1.1 sat out there. It became an RFC in the late 90s. And after that, there was an immediate effort to say, okay, well, this is obviously held together by baling gum and spit, baling wire and bubble gum and spit and so forth. And we need something better, something that has more reasonable engineering behind it. And an effort was started called HTTP-NG, which was in the W3C, and it was trying to create a more network-friendly binary protocol that used the network more efficiently and had a more of a solid architecture behind it. That never really went anywhere. I think that the implementers of HTTP, after all of this work around HTTP 1.1, and all the experts, a lot of the experts as well, were pretty exhausted. And they never really got the energy together to go and come up with this further revision of the HTTP protocol.
So when was that? When was the HTTP-NG effort started?
It was around 2000, I want to say. That's a great question. It was, so my involvement in standards started around 99 and 2000, and I think it was just around then that it was really happening. Let's take a look here. It had some interesting ideas, and there were a few proposals put together. What's interesting about HTTP-NG is that some of the folks behind that, including Henrik Fredrik Nielsen, went on to come up with proposals like PEP, the Protocol Extension Protocol, I believe. And that eventually turned into what became SOAP and Web Services, which was an interesting ride, but I'm not going to bore people about SOAP on this interview, I don't think.
We'll see. If we have time at the end.
We'll see, yeah. Okay, here it is. HTTP-NG. Yeah, actually, sorry, they started in mid-97, first drafts in mid-98, and then by late 99, it was kind of ramping down. They realized it wasn't going anywhere, I think. And I didn't directly participate in that stuff. I was around the edges a little bit on that, but my involvement came a bit later. I chaired some working groups and worked in some working groups kind of around HTTP. And then in kind of the mid-2000s, 2005, 2006, it became more and more apparent that HTTP was sort of rudderless. We didn't have a very strong community around the protocol. We didn't have somewhere where all of the implementers were discussing the problems that were coming apart. But we knew that we were having problems. I was working for a while on Squid, the web proxy, and seeing a lot of problems in terms of HTTP interoperability there. And so talking to the different implementers and talking to the other stakeholders, we decided to start a working group called HTTP BIS, which is the one that I chair. And the idea behind that was just to sit down and redocument, to write down again what HTTP is. And so RFC 2616 was the outcome of the HTTP 1.1 effort, and that sat for many years. And so what we did was we took it and we picked apart RFC 2616 and we started, writing down issues. This needs to be clarified. That doesn't make any sense. This part of the document conflicts with that part of the document. Because remember, it was written down in a hurry. It was written down by many people. And what happened was that throughout the 2000s, especially after we had things like AJAX, XML HTTP request, people started really pushing the boundaries of HTTP as a protocol. It wasn't just go off and, get me some HTML and CSS and eventually JavaScript. It was, and maybe post a form. It was doing a lot of much more interactive things that really pushed the limits of performance on the protocol as well as the semantics in terms of, what does the protocol mean when you combine these different things, or how is this corner case handled? And so we went to write down these specifications more clearly because we realized that, people were coming to people like me or to Roy Fielding or Julian Reschke or a few other people and asking these questions again and again of how does this work? And we decided to write it down instead. And so HTTP BIS turned out to be a multi-year effort. We only finished it a little while ago. I guess, about a year and a half ago? And that's because it was really a part-time project. It was, primarily myself and Roy Fielding and Julian Reschke taking the time to pick through everything and eventually rewrite many parts of the specification, to modernize it, to make it more clear to read. I was the chair of the working group, but I also took editorial responsibility for the caching section. And I vividly remember, when I decided to rewrite the section pretty much from scratch, because I realized that there were certain things that were repeated 3 or 4 different times in different parts of the document in 3 or 4 slightly different ways, which is, it's horrible for interoperability. Mm-hmm. And when I was able to do that, the first thing I did was I ripped something like 10 pages out of the specification, because there was this repeated, slightly different text, which was very liberating, I suppose. And so that's the process we went through there. In doing so, an interesting thing happened. We had more and more HTTP implementers, folks from Firefox, Chrome, Microsoft, Apple sometimes, CDNs, servers would come along and ask questions and get involved. And we slowly started rebuilding the HTTP community, which, when you have a protocol that's so critical to the operation of the web, it's really good to have the implementers talk to each other. And so that, for me, that's kind of the ulterior motive of that work, was getting people to talk to each other. And so we published the RFC 7230 and its companion documents. I blanked out a large part of that because it was such a big part of my life.
I don't think it was that long ago, but I may be mistaken.
June 2014, you're right. It wasn't that long at all. We published those documents, and they collectively redefine HTTP 1.1. And so when you refer to HTTP 1.1, these documents are the authoritative documents. It's not a new version of HTTP, it's just written down differently. And we split it up into, how many did we end up with? 6, I think?
6.
Yeah, 6 different documents. We used to have 7, then we collected it down into 6 at kind of the last minute. And we split it up because, the RFC format, it's still in ASCII format. There's some work on changing that going on right now. But the option we had was, okay, we can publish one huge ASCII document and have people try and navigate it, or we can split it up into different logical parts. And we opted for the latter. sometimes, talking to the editors, I think sometimes we could have, and Roy's made this comment a few times, we could have just recombined them and published it as one document. It was really picking it apart into the components that was the important thing. And so it's much more modular in that fashion. So that was useful.
So that was a huge effort, or at least it seemed that way from the outside, and it's a huge document or a huge set of documents with a huge number of pages. I don't know how many pages is it? Like 200, 300? I have no idea.
Yeah, it's more than 200 because I think 2616 was 200 pages if I remember. It was more than 200. I think the document set is bigger mostly because there's a lot of repeated boilerplate between the documents. Mm-hmm. There were some things that we had to explain in a lot more detail, because it was kind of elided, because it didn't fit the use case for the web back in, the late 90s. 2616 was published in June 1999, but most of the work was done before that, substantially before that. Yeah, so 2616 is 176 pages. I think our document set is like, someone said 280, 290, mm-hmm. rings a bell, I think. And like I said, a lot of that is repeated boilerplate. But it is more navigable. It's much more self-explanatory. And the feedback we've gotten from implementers is that it's a lot easier to understand how to implement HTTP correctly. And that was the goal that we had. Mm-hmm. So yeah, it was a big effort. It took a lot of energy. Sometimes, we have a graph somewhere of kind of, commit activity on the repo. And there were definitely a few periods where it was pretty quiet. And then Julian and I and Roy would get together somewhere, Roy's house or in Germany to visit Julian. And, you'd see this spike of activity, and then it'd kind of, calm down a bit as we incorporated feedback from other people in the working group and talked through everything. But, we got it done. I don't think we have a lot of appetite to do that again. Although Julian does want to, relatively soon, I think, take that document set and make it a full standard. So, right now the HTTP documents, the IETF has gone to a 2-level standards process where there's proposed standard and full standard, and they're proposed standards. Or is it draft standard? I always get mixed up. They change it so often. But we want to take them eventually to full standard because, they're a cornerstone of the way the internet works today. So when we clean them up a bit, and probably when we do a little work to incorporate what happens in HTTP 2, and get a little bit more errata collected and so forth, we'll probably revise these documents one more time and publish them mostly in the form you see them today, but with a few improvements.
The one thing that I'm personally really happy about is that they still read like specs and not like pseudocode, as, for example, the HTML spec does these days.
Yeah, that's a contentious issue. They are more algorithmic than they used to be. We definitely added some more of that. And I do have a lot of sympathy for what working group guys and the HTML5 guys have done, and girls, I should say, in that it is, it's important for interoperability to specify things as closely as you can. And if you do it algorithmically, if you say, do this and let this be this and then that is that, you really do assure interoperability even around all the corner cases.
Yeah,
on the other hand,
make it pretty much unreadable, right? So that's the downside of things.
Well, yes, you do have to, be able to read that and keep the state in your head. And so as someone who just wants to casually look at the document and say, well, what's the syntax of this or what does that mean? It's a lot harder to do. I think their response to that would be, well, this is where the user guides come in, or the books or the tertiary material. And the point there being that if you specify it both ways. If you say, here's the algorithm and here's what it means, in prose, then there's the chance for mismatch. And unless you're very, very careful about making sure you mark which one is normative and, looking for consistency there, it's much more likely you're going to specify ambiguous things, or one of your implementers will look at the prose and take something else away, and interoperability will suffer. And of course with the web, often security will suffer. And so I do have a lot of sympathy for that approach, but yeah, it sucks. It sucks as a reader. And it's also, if you want to reuse an artifact for something else, if you want to repurpose it, that whole, unintended reuse, axiom that Tim talked about, then it's a lot harder to have unintended reuse when something is specified as an algorithm like that.
Mm-hmm. Okay. So we got through the versions, including the new version of HTTP 1.1, which took a long time to be finalized. And then Speedy came along.
Yeah.
Is that a correct statement?
So Speedy came along. I remember I was visiting the San Francisco Bay Area, and I got an email from someone I didn't know, a gentleman named Mike Belshey, and he wanted to have dinner with me. And so I went out, and he kind of gave me a tantalizing, I have some interesting stuff about HTTP I want to talk about, and he worked for Google. So, okay. So I went out to dinner with Mike, and he laid out what he was doing with Speedy. He's, him and Roberto Pion are the two core authors of Speedy. And I remember vividly just getting a huge smile on my face because what he was talking about made a lot of sense. And it was so much in line with things that Roy had talked about when he was talking about Waka. So Waka is a protocol that Roy Fielding has talked about for a long time, an HTTP evolution or replacement protocol. But he's never written down, unfortunately. But from, just being around Roy and talking to him about it, I kind of could intuit enough about it to say that it sounds like Mike is in some ways going down the same path. And so we did that, and he gave me a copy, I think, of the Speedy spec, or I looked at it when they did the release. This was just a few days before they made the public announcement. And what intrigued me was that I was able to look at their spec and go and take a Python HTTP library that I'd written, from sockets up, and rewrite it to talk Speedy in, 2 days of kind of, part-time doing other stuff kind of, time frame. And I was able to interoperate with Chrome because they'd put it in Chrome. And that to me said, wow, this is, amazing. It works. You can write an interoperable implementation from the spec. And looking at my code, HTTP 1.1 is a textual protocol. So it's all, here's a header field, and here's a colon, and you have to split on the colon, and here's the value, and then there's a new line, or maybe it's a /r/n, and there's another one, and there's a blank line, and then you have the body. So you have to do all this parsing to figure out how HTTP 1 works. And in that parsing, there's a lot of error handling or corner cases in that, well, what if there's white space here, or does capitalization matter there, or, there are all these different kinds of cases you have to handle. And in fact, HTTP 1.1 has 4 different ways to figure out where one message ends and the next message begins, which is incredibly complex. And so if I looked at the code base for my HTTP 1 implementation versus Speedy, the Speedy was a lot more compact. It was significantly smaller, much easier to read, more efficient, so forth and so on. And so as an implementer, that's a joy when you have, a binary protocol. Yeah, that's not great from the standpoint of debugging it because you have to have some tool to help you debug it. But from an implementer standpoint, you're much more confident about your implementation quality if you don't have to worry about all those corner cases and all that text parsing when it's just, here's the binary, and if you get your parsing wrong, you're going to know it because everything's going to go up in flames.
So let's talk a bit about what Speedy actually improved upon or what problems it addressed. So one thing that you mentioned now is the textual nature of HTTP 1.1, and Speedy obviously recast that in the form of binary frames, so as opposed to,
yes,
as you just explained. What else was new in Speedy?
So the biggest change was that once you have this binary encoding, you can split up HTTP messages into those frames, and each of those frames has what's called an explicit stream identifier. So in HTTP 1.1, when I have a request and a response, they're on the same connection, and I know that request is associated with the response because of the ordering. I send request number 1, and then I send request number 2, and I get back response number 1 and response number 2 in that order. That's just how it works. But that makes it so that you can't reorder the requests and responses. If the server, can't get response number 1, or it has to think about it a lot, or it's really, really big, that means that response number 2 is blocked until response number 1 is complete. And that's called head-of-line blocking. And that means that, for that and a few other reasons, but mostly that, browsers don't just use one TCP connection to talk to a web server. They use somewhere between 4 and 8 connections. And what they do is they use those multiple connections for parallelism. They'll say, okay, I'm going to put this request on that connection, and in case that blocks, I'll use this other connection for the next request. the problem with that is that if you look at the statistics, an average web page these days can have somewhere around or even more than 100 different things to load. JavaScript, CSS libraries, images. There's a lot going on in the modern web. And if you've only got between 4 and 8 connections, that means you still, as a browser, have to make choices about which connection you use for which request and at what time and how to order them. And so the browsers use a whole bunch of heuristics to figure that out. And usually, actually, surprisingly often, they do a pretty good job, but often they can't because they don't have enough information. What HTTP2 does is because you now have this stream identifier where you can explicitly associate a request and response. You know that they're related because of this little identifier. And because you can chop up requests and responses into frames, so you don't have to keep one request altogether, you can interleave requests and responses and parts of requests and responses at will in both directions on the connection. So now all of a sudden it's what we call a fully multiplexed protocol, where you can send any part of any request or response at any time. As you've got these buffers you need to drain. And that frees up that head of line blocking problem. And so that's a lot better. The goal in Speedy and eventually HTTP2 is to only have browsers use one connection to talk to a given web server. And so that's the really big change in Speedy and later in HTTP2. The other interesting things are that if you look at traces of modern page loads, you'll notice that there's a lot of repeated information in HTTP headers in both directions. And that has a negative impact on performance as well, especially on the request side. If request headers with things like cookies get really big, then it takes longer to even get the requests to the server so the server can start serving them. And so Speedy introduced header compression, where you can actually just compress the headers as they're being pushed out on the wire. And that's separate from compressing the bodies, by the way. There's what happens is there's a compression context just for the headers on all the headers on the connection in one direction, and that gets reused for every request so that you can learn what headers are common on that connection. If you send a cookie once, you don't have to send it again. You can refer to the cookie you send the first time.
Mm-hmm. So obviously Google had started doing this for their own purposes. So they obviously benefit from the protocol being more efficient, given that they probably run the largest set of servers in the world. So one of the things that I seem to recall is that they actually deployed it and tried it out before telling the world about it. Is that a correct recollection?
I believe so, yeah. They had it running in Chrome. They had it running on GFE, which is the Google front-end server. Mike worked for Chrome and Roberto worked for GFE, so they were working together. That was a collaboration between them. Then they brought data. They brought data to the table and said, we think that this is interesting enough to talk about with the community. And so I think it was the following year that Mike came to an IETF meeting, and I gave him some time in the working group meeting to present what he'd found and to kind of give a heads up to everyone in the community that, this work was going on. I mean, obviously most people knew about it, but it was important to get the conversation going in the working group. And then a little while past that, I think the next probably notable thing that happened was that Firefox shipped an implementation of Speedy as well. And that's really when people sat up and took notice. They realized that this isn't just a Google thing. If the engineers at Firefox thought that this was interesting enough to spend their time on implementing, that's a really big statement. We saw interest from other folks. We saw eventually implementations from folks like Nginx and other servers. And it was very clear that momentum was building. So, from the standard standpoint, we had a choice. We could either let Speedy become a de facto standard in the marketplace where, whatever Google said it would become. Or we could try and bring it into the standards bodies and have a wider community of folks take a look at it and give their input and make sure that it reflected more people's needs. And so talking to folks inside of the ITF, we thought that was a good idea to try to do that. Talking to Roberto and Mike, they were willing to bring it to the table. I think Firefox was encouraging them to do that quite strongly. And so we ended up holding a process where we said, right, we're thinking that we see enough in implementer interest and deployment interest in a newer version of a protocol to serve the needs of HTTP, that we want to start talking about that in the working group. Does anybody have any proposals for that sort of thing? And we ended up having 3. We had Speedy from Mike and Roberto. We had a proposal from Microsoft. And we had a proposal from, 3 or 4 intermediary implementers. So folks who make web proxies or reverse proxies. And the working group talked about that for a while. Speedy was by far the one that was, most well specified and fully fleshed out and had experience behind it. And also it had the most support by all the implementers who came. So we chose Speedy as the basis of the work. But when we did that, we rewrote the charter to start work on HTTP2 using Speedy as the basis. And we were very careful to point out that it's not, choosing Speedy by default. This is the starting point. And we're going to talk about everything in this document. And we're going to make sure that the working group agrees on everything in the document. And if the working group doesn't agree, we'll pull it out. Or if the working group comes up with a better way to do it, we'll put it in. And so we were chartered to do that. I wanted to keep a fairly aggressive schedule for standards. We chartered to do it in about 2 years. That's very aggressive for standards work, and it's glacially slow by most developers' standpoint. But trust me, that's fast for standards.
Well, if it's compared to the time it took you to get HTTP 1.1 revised, that it's really fast, because it was much faster to do a new protocol than to revise the old one, right?
Right. Well, yeah, and that's kind of apples and oranges, just because that was a very much a part-time effort. That was, a bunch of us on the side saying, "Oh, what do you think about this? Does this make sense?" And whereas HTTP2 had a lot of momentum behind it. There was a lot of very strong implementer interest. We had a lot of resources put into it from the get-go. So we chartered to do it in 2 years, and I did that. Really, my argument in that kind of schedule was, we've got a tremendous amount of implementer interest. They've come to the standards bodies in good faith, put some of their really talented engineers up for it. If we take 5 years of arguing in committee about this, or 10 years, or, there are lots of examples like that, we will lose their interest and they'll walk away. And that means that the effort will be dominated by people who have opinions but not running code. So we kept it time limited to make sure that we could have that audience's full attention for a bounded amount of time and have their input and turn it into the best document we could in that amount of time. So it took about 2 years. We started work in earnest, I guess, in December. And the next June, July, we had, I think, our second or perhaps third face-to-face meeting in Hamburg. And that was our first, what we said was an interop event. We'd put out a few drafts before then, but this was the first time we'd said, okay, here's a draft, and we think this is good enough for people to go off and actually do an implementation of. And we'll do interoperability on that and do some testing at our next meeting. And so people had 6 weeks or so to come up with an implementation. And I was hoping we'd see maybe 3 implementations show up in Hamburg. And we ended up having 10, that's when I really knew we were onto something. I knew that this was not just committee work and a bunch of people sitting around a table talking. This was a serious effort where people were writing real code. And so that was a really good sign to me. That made me feel a lot better about it. And then we spent the next year and a half on a bit of a roller coaster hammering out the document. We had to rip out the compression mechanism that Speedy used because it wasn't safe. They found an attack against it. And then we had a competition effectively to choose a new one with a few different proposals that ended up being combined. Went to last call last year. Had a bunch of people raise a bunch of fairly big issues about it at that last minute. And so we had to talk through those. That took a few months. Came to conclusions about it that people were, a lot of people were unhappy about. And I think, the rule of thumb is that when everyone's unhappy, that's consensus. And took it to the IASG late last year. The IASG is the body in the IETF that formally makes decisions and approves documents. It's a council, if you will, of people who run the different areas in the organization. And they have all but approved it as we speak. So I'm hoping that we'll have an RFC on HTTP2 pretty soon.
Okay, so we can probably assume, or we can hope that it'll be an official document or an official standard. Well, as much as official standards are released by the IETF by the time our listeners listen to this episode.
I can only hope so.
Yeah. So
I could record two different, endings for this if you like, if that'd help.
No, it's fine this way. So let's talk a bit about the technical stuff we haven't touched upon. So first of all, maybe we can finalize this discussion about SPDY and HTTP. So for all purposes, we can assume that SPDY will be subsumed or superseded by HTTP2. It seems that even Google has agreed, or
yes.
Even Google has agreed to that as well. So the goal is to go with HTTP2 only, correct?
Yeah, they announced that on their blog, early 2015. They've been telegraphing that intent to the working group for a very long time, that their intention is to move to HTTP2 as the standard. So that's not a big surprise, I think, for most of us in the working group, but it's really good to see. I think they announced they're going to turn it off in early 2016, so we'll see if they meet that schedule. Changing protocols on the server side is always kind of a nightmare. So, if they don't meet that by the day, I'm not going to be horribly disappointed. The momentum behind HTTP2 is pretty clear. So we're pretty confident it's going to get a good chance in the marketplace.
Okay, so we talked about some significant changes. So the reuse of a single connection is one, the binary protocol, the header compression is one. Is there anything else that's new in HTTP2 as opposed to HTTP 1.1?
Another thing that's worth touching on is server push. The idea that the server can push a response to the client. Usually you can think of it as the server pushing something into the client's cache before the client realizes it needs it. And that's just to avoid the round trip. You think about when you load a page, the client goes and gets some HTML, the server sends back the HTML and parses it for all the links and then starts requesting all the different linked objects. But if you think about that, the server just sent the HTML. It knows what links are in that. Why can't it just start sending what it thinks the client is going to need? And so server push is an optimization to try and avoid that round trip. I think most people would be happy to admit that it's the most experimental part of HTTP2. How it's going to be used in real life is still a bit of an unknown. It's especially uncertain because it's the one part of HTTP2 that really requires, it doesn't fit into a normal HTTP1 API. So everything else in HTTP2 you can map onto an HTTP API. And when I did my library, you use the same API for the client and the server. You're still using HTTP methods and headers and bodies and status codes and everything there. None of that changes. It's just how it gets put onto the wire is different. But with server push, it's a different thing. It's the server sending it's kind of like sending a synthetic request response pair to the client proactively. And how that's going to get put into code and people are going to think about it and how it's going to be used, we'll see. It'll be interesting. I know that in HTTP 1.1 there were a lot of kind of last minute or extra features put on that didn't work out in the end because they weren't mapped well onto the existing code bases. Things like pipelining or the expect continue function. They've never really worked well. And personally, I think that part of the reason why they've never worked well is because they were tacked onto the protocol like that. They didn't fit within the core base, the core footprint of the protocol.
So I would assume that for the client, it should be pretty easy to reuse the same API, correct? Because they just get an answer to a question they haven't asked yet. So if they ask the question, they get the answer. But on the server side, it's obviously different. Right.
Server side is definitely different because you have to push, and that's kind of a new thing. On the client side, it could be the same. It could be that it gets pushed into your local cache, and look, it's already there. That's great. But people are already talking about ways to use or maybe abuse server push to do other things, to kind of build eventing on top of HTTP and server pushed events. And that means that you do need something to get a notification. So we'll see. I think it's fascinating to see how it's going to be used. It could fizzle and turn into something that is only used for corner cases. It could be the basis of a lot of exciting new stuff. I think we're just going to see.
So the one question I always have about this feature is, what if I don't want the server to push the stuff because I'm not using it? So
yes, you can turn it off. So you can either turn it off altogether and say, I'm not participating in server push, don't push me stuff, and if you do, I'm going to shut down the connection. You can also refuse a push. You can say, okay, the server starts pushing you something, does a push promise, you can say, okay, I already have that in my cache, or maybe I'm a web spider, I don't need it. And you reset the stream. And that's one of the new bonus features in HTTP 2 that's really good. In HTTP 1, if, let's say you start a big download, or you're getting something quite sizable from the server. If all of a sudden you don't need it, maybe the user's navigated away from the page, or maybe, they cancel a download or whatever, you have no choice but to shut down that connection. You have to eat all the bytes that are being sent to you. In HTTP 2, you have a mechanism called reset stream, whereby you can say, you know what, that stream, that one request response interaction, I'm not interested in it anymore, shut it down. And you can do that without sacrificing the entire connection. So that's good from a performance standpoint because, you don't have to reconnect to TCP. If you're on HTTPS, you don't have to do a new SSL negotiation. You can still just reuse that connection and get the most out of it. So reset stream is helpful there. And you can use that if somebody starts pushing you something, you can say, nah, I don't want that one.
So in terms of terminology, the stream you're talking about is basically the virtual connection, right? What used to be the connection in HTTP 1.1 becomes a stream in HTTP 2. Is that correct?
Not exactly. I guess the best mapping is it's the connection in HTTP 1.0 without keep alive. It really just identifies a single request response pair. And that's it.
Okay. Understood. Thanks. Good. So, one of the reasons, again, that is something that I seem to recall, and I'm happy if you can correct me if it's wrong. I seem to recall that one of the reasons Google was able to try out Speedy in practice was that they simply used or mandated TLS for everything. So everything was encrypted and nobody could tell what they were doing, and no intermediary was confused by anything weird going over that HTTP connection.
Right.
How is that done in Speedy versus the way it's done in HTTP 2? And is it mandatory in HTTP 2 as well as it was in Speedy?
Right. So yeah, Speedy used TLS for a couple of different reasons. One was interoperability, as you say, in that there are a lot of boxes out on the internet that when they see something on port 80, they assume that it's HTTP 1.1. And that assumption can make things break in really awkward and unpredictable ways. So you get much better interoperability from those middle boxes if you're encrypted. The other reason is that even back then, in 2009 when Mike and Roberto were working on Speedy, there were a number of attacks on the web where, passwords, authentication tokens, personal identifying information were going in the clear. There was an attack called Firesheep where you could go into a, cafe and turn on this piece of software, it was a little Firefox plugin, and sniff people's passwords going by, or their authentication tokens for places like Flickr or Yahoo or Facebook or whatever, and then log in as them, and become that person in your browser. And that's because people weren't using SSL. They weren't encrypting their connections. There were also incidents like, I think in Germany, Google had the Street View incident where they were accidentally, for some value of accidentally, sniffing Wi-Fi passwords as they did their Street View, drive around neighborhoods. And that data was captured, and that was not good as well. And so when they thought about this, I think especially Mike took a somewhat principled position and said that, look, we've got this new protocol, and it can level the performance issues with using HTTPS to a very large degree, or even provide better performance over TLS than in HTTP 1.1 without it. It seems like a great opportunity to level up security in the web, to hold out as a carrot and say, if you want to use this new protocol, for all of those reasons, and as well as for the interoperability reason, we're only going to implement it over HTTPS. And this was all pre-Snowden. That Snowden happened afterwards. And so that was for Speedy, and that made a lot of sense. We had that constraint kind of grandfathered in implicitly when we took on HTTP 2, but it wasn't explicit in the spec. And we started to talk about those issues and whether we should require HTTPS to use HTTP 2. And in fact, Snowden happened during that. One of the big Snowden leaks happened the day before one of our working group meetings in Berlin. And we quickly kind of reconfigured our agenda to talk about that and what that meant for HTTP, because they were targeting HTTP explicitly. In the end, after a lot of discussion, there were enough people in the working group who said, well, HTTP is used for the web, sure. It's also used for a lot of other things. It's also used for back-end systems and for APIs and for non-critical data in their views. And we couldn't get consensus to require HTTPS for HTTP2 because of that. There were enough people who felt that way. And critically, as working group chair, I didn't really have a mechanism to make a judgment call about it. In the IETF we say we have rough consensus and running code, and we make decisions based upon technical criteria. We didn't at that time have the technical mechanisms in place to say that, encryption is something we really need to provide as a baseline requirement. The other factor there was that our charter said that HTTP2 had to be usable for all existing uses of HTTP. And that would include HTTP URIs. We have a technique that we've talked about to encrypt optimistically or opportunistically encrypt HTTP URIs, but that was controversial as well. And so we were in this place where we didn't really have a clear way to meet our charter and to make a technical decision where we could go and say, yes, let's make HTTP2 encrypted. At the same time, Firefox and Chrome had made very strong statements that they would only be supporting this over TLS. Chrome has said only HTTPS. Firefox has said we'll do HTTPS, and we're going to fool around with the opportunistic security mechanism and try that because we think it's an interesting thing. But neither of them are going to do it in the clear. Other browsers haven't made those statements, but between the two of them, they have a tremendous amount of the web browser market, and that can actually change the dynamics of the overall deployment of the protocol. And so, we were faced with a choice. We could either spend 6 or 8 months, maybe a year, maybe delay the protocol indefinitely, trying to hash out some sort of compromise position or consensus around encryption on HTTP, or we could let the market sort it out, knowing that these browsers are making their own decisions already. And it seemed like the pragmatic thing to do was the latter. And so that's where we left it. Having said that, I personally would have loved to have seen it become encrypted only. We've been doing work in other places to try and improve the quality of encryption on the web. And indeed, so the other body I mentioned at the beginning of the technical architecture group, we just released what we call a tag finding, a kind of an architectural statement saying that we need to secure the web. So if we can't attack this problem from the standpoint of making HTTP2 encrypted in the standards, we're looking at in the W3C, how do we encourage more use of encryption? How do we level the playing field so that encryption is easier to use, so forth and so on. And so we're making progress on that front.
Well, I can understand some of the reluctance in accepting a TLS only or encryption only way of doing things because of the communication between backend servers that just happen to use HTTP
Right, but back-end servers are a big target for state actors, so...
Okay, true.
And that was one of the arguments that came up again and again, and it was interesting to see that argument would be made, and then a few weeks later, a new Snowden release would be made where they'd say, oh, look, we've gotten into these back-end servers. Mm-hmm. And then all of a sudden encryption becomes more important.
Fair enough. So one of the things that I, again, seem to recall is that Google used some hack with Speedy to initiate the SSL or the Speedy connection. How has that been affected by the standardization HTTP2? First of all, is it correct, and what happened to it?
So there's a couple of ways that you can initiate HTTP2. For Speedy, they had two mechanisms. One was if you're already on an HTTPS URL, they used what was called NPN, or Next Protocol Negotiation, which is a modification to the TLS handshake or an extension to the TLS handshake, which says when you finish the TLS handshake and have a secure connection, the next protocol we want to talk inside of that connection is this one. And that's how you can advertise support for HTTP2 or for Speedy. And HTTP2 has a similar mechanism. It's just gone through the standards process. It's a little bit different in its properties, but it's called ALPN, or Application Layer Protocol Negotiation. And that's in OpenSSL now. It's getting more prevalent. The other mechanism for discovering and negotiating Speedy was alternate protocol, which is an HTTP header that you would get that kind of hints and says that if you want to talk this new protocol, you can do it over on this port over here on the same server. And we have a very similar mechanism that's a little more general and usable for other things called alternative services, which we still have as a draft and we're working on still.
Okay. So maybe let's talk a bit about the consequences. So we kind of assumed, or it was kind of the unspoken assumption, that if you switch to HTTP2, you get some benefit in terms of efficiency and speed. What is actually the basis for that assumption? Were there some tests made, and if so, what are the results, and what can users expect if they move to HTTP2?
It's hard to quantify. It depends so much about how you use the protocol and how the browser implements the protocol. The early feedback I've gotten from most of the implementers is that, generally speaking, you'll see somewhere between a 5 and 15% performance improvement just by turning the protocol on. And that's not for every connection, but it's for most connections. There will be cases where you won't see any improvement, or it might even be a tiny bit worse. And there have been a few interesting academic papers out there about that and how that works. The interesting part comes when you tune your web content a little bit to take advantage of it, and you tune your web server. So, we have all these different techniques for performance optimization in HTTP 1.1. And if you participated in the web performance community over the last couple of years, conferences like Velocity, the mantra has always been reduce the number of requests you make. And that's because there's so much overhead to requests in HTTP 1.1, because the browser might have to spool up a new connection, or that request might be blocked by another request before it, or vice versa. Yeah. So what's happened is that there are a bunch of what are effectively hacks that we use for performance optimization in HTTP 1.1. In that, we have things like CSS inlining, CSS spriting, concatenation of different parts of JavaScript into one big download. And all of that is to fulfill this mantra we hear in the web performance optimization community, which is reduce the number of requests, avoid that overhead of an individual request. Well, in HTTP 2, you don't have the overhead nearly as much. You have multiplexing, so you don't have to worry about head of line blocking, and you don't have the massive headers for each request. You have header compression that are making those much, much smaller. And as a result, individual requests don't have nearly as much overhead. It's almost not noticeable. And so if you phase out those hacks, you can tune the performance of your site back to something that's more interactive and smoother. The anecdotal evidence I'm getting is often performance with HTTP2 is smoother. There's less variation from load to load. It's just a better experience for the end user. So 5 to 15% is kind of the guideline number you'll get as a rough starting point. Then you get folks who are doing a lot of optimization and really building their sites to take advantage of the new protocol. Google has cited numbers of around a 44% performance increase, especially on high latency connections, I think. Twitter had, I think, similar numbers. Twitter was different because they were using Speedy and HTTP2 a lot in their mobile clients. So this wasn't a browser client. This is, a mobile app that is doing the HTTP requests. But if you think about it, if you're requesting a lot of information, through an API, and you can make it a lot more granular because there's not an overhead to the requests, you can get much better performance than using HTTP 1.1. So that kind of makes sense. I think we'll see over time. I'm expecting that as the protocol gets deployed, we'll see more best practices come out of the web performance community. We'll have more tools to analyze performance and a better understanding of how to get the best out of it. And the open source implementations will continually improve themselves so that we have a decent out-of-the-box performance. A lot of what HTTP2 does is, I talked before about all the heuristics that a browser uses to decide which request to make at what time on what connection. Well, the idea in HTTP2 is that as much as possible we move those heuristics out of the browser. The browser isn't trying to predict how the page is going to perform. It all gets put onto the server. And the browser sends information about how the page is loading in the form of what we call priorities. But the server makes the decision about what response to send at what time and in what proportion, and how to prioritize those. And a lot of I think the potential benefit is in terms of, those decisions that the servers make. So it's kind of taking performance out of the browser hands, at least partially, and then giving it over to the server to make its own decisions.
So you mentioned those hacks that people have been using for a long time to make HTTP 1.1 fast for websites. Is it correct that those hacks actually hurt you when you're using HTTP 2?
They certainly don't help you. You think about it, if you're downloading a very large JavaScript library because it's all been concatenated together and you're only executing, 10% of it for the actual page, then that's inefficient, because, from the browser standpoint, while you're loading that JavaScript, unless you're doing an async load, the world stops. And certainly while you execute it, the world stops, and that's bad for performance. Also, if you want to change part of, your CSS sprite or your JavaScript, there's just one line you need to change or one image, then again, because it's all lumped together in the HTTP cache, you have to invalidate the entire cache and re-download it. One way to think about it is that, what we've kind of been doing slowly but surely is turning the web into these single page apps. And I don't mean that in the sense that it's just a single page that you navigate. I mean something more like Flash or PDF, where you have to download this huge chunk of stuff just to get a functional page. And that's not a very web-like experience. PDF has the ability to navigate. It has linking. You could build a web out of PDF, but nobody really does that because it's so clunky and you have to wait so long for things to load. HTTP 2 has the promise that we can make things more granular again.
Mm-hmm. So for practical purposes, it'll obviously take some time until, first of all, HTTP 2 is finalized, then until it becomes part of the browsers, and then until those browsers gain significant market share. So HTTP 1.1 is obviously there to stay for a long time, right? So what is the way to deal with that? Do you expect people to build for both, or build primarily for HTTP 2 and for HTTP 1.1 only for backward purposes, or doesn't it really matter as much as I make it sound?
I think it's going to be a little faster than you think in that both Chrome and Firefox have the code ready to go. Firefox is very excited about this. I think both of them are at the point where they just have to change the protocol identifier in the negotiation from the draft to the final version, and then put it through their release processes. And, we have these evergreen browsers now where, they're releasing every 6 weeks. And so we'll see them upgrade quite quickly. I know that the IE team is very impatient to match or at least get in the ballpark with those kinds of schedules. They want to compete there too. And so I think we're going to see an appreciable part of the browser market move to the new protocol quite quickly. Having said that, there is going to be an overlap period. There are always going to be servers out there that, run HTTP 1.1, and that's fine. From a server operator, from web performance standpoint, I think we're going to see a number of different strategies based on the needs and the capabilities of the sites. Some sites will just leave it all spreaded and inline and concatenated until it's so obvious that they need to switch over based on their metrics. They'll just do it one day. Some sites will do it proactively and take the performance hit for the old browsers. And some folks will, put a FEO solution in front or some sort of intermediary that, makes the decision on the fly and re-encodes the pages, whether it's, mod page speed or whatever to serve the client, each individual client as best they can. It'll be interesting to see which strategies, give the best results.
Mm-hmm. Okay, maybe a final question. All of this work you've been doing within the HTTP working group in the past years has been sort of under the hood, right? First, the revision of a specification without actually updating the protocol, and then updating the protocol, but mostly updating it in a way that makes it completely transparent to the actual application developers, right? So there have been different kinds of changes, and I'm not downplaying it in any part. It's a huge effort, and it's a huge achievement. But do you expect something to change in the actual protocol semantics anytime soon? Are we looking at new verbs or a new optimization or any other more significant change to HTTP, or is it here to stay the way it is for a long time?
That's a great question. There's that kind of semantic footprint that HTTP has a request and a response, and the request has a method and the response has a status code, and you've got headers, and you're right, none of that has changed. We've tacked on a few headers now and again. Occasionally we have a new status code or we have a new method like patch, but it's still very recognizable, from the APIs you use and so forth. I've been talking to a bunch of folks in the community about, what next steps might be. There are a bunch of intermediate proposals for things like new status codes. whether it's the 451 status code that Tim Bray has proposed or some other stuff. I think we're going to continuously see that, low level adding extension point kind of stuff. But I've also heard some people interested in, okay, what would the benefit be if we started fresh and we said, what does it take for a browser to load a web page? What does it need from a protocol? And what benefits could we do if we started from scratch? I don't think we're going to see that anytime soon, but it's an interesting thought experiment to see where that might lead.
So, what is a good way for listeners to start familiarizing themselves with the whole topic? Is it to read the HTTP2 spec, or do you have any other good starting points people could look at?
Starting points. So on the HTTP2 homepage, it's http2.github.io. There's a FAQ there. That's probably a good place to start. And there's also a section on the homepage, what is HTTP2? Another great resource is Daniel Stenberg, who's the main author of curl. I hope everybody knows curl. Has gone and written an HTTP2 guide, kind of a primer, and it's a PDF on his website that is a really fantastic resource. He's been updating it as we've gone along. Daniel's participating in the working group as well, and he's been a great participant. And so you kind of get this fly-on-the-wall perspective on why the protocol is the way it is, how to use it, what it is, how it works. And that's a great introduction, I think.
Excellent. So, Mark, it's been a pleasure talking to you. Thanks a lot for all those insights. And
no worries.
Thanks for doing this.
Thanks so much.
This is Stefan Tilkoff for Software Engineering Radio. Thank you for listening.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more information about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can write comments on each episode on the website or write a review on iTunes. Mention or message us on Twitter at SE-Radio, or search for the Software Engineering Radio Group on LinkedIn, Google+, or Facebook. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under the Creative Commons 2.5 license. Thanks again for your support.